Okay, the last time we left our code in a state that compiles and runs, but we don't really know why. So we have to actually explore what's going on this line here, and more importantly, what is this @mute that we have before our input. So to do that, we have to explain one of the most important features in Rust. So strap in, because this one will be intense. In this video, we'll talk about ownership. It is a simple concept to explain, but it has huge implications for the entire language design of Rust. It is a concept that is absent from most other languages, and it takes some time to start thinking properly about it while programming. So there are 3 ownership rules in Rust. So the first rule is that each value in Rust is owned by a variable. So everything has an owner. The second rule is that when this owner goes out of scope, the value will be deallocated. And the third rule is that there can only be one owner at a time. These are the 3 simple rules. They seem pretty straightforward, so let's actually explore them. In our example here, we create a new string, and this string is owned by the input variable. So this input here is the owner of our string. So far so good. The string lives on the heap because its size is not known at compile time, and on the stack we only store a pointer to the heap plus some additional metadata like the size of the string. This is just a pointer to our string pretty much. And when this input goes out of scope, the string on the heap will be deallocated. This sounds very familiar to the smart pointers that we have already discussed in the previous section. So the string is a type of a smart pointer, pretty much. And to add a little bit more detail to this, the Rust compiler will call the drop function on the string when its owner goes out of scope. So when this function exits, the drop function on the string will be invoked automatically by the compiler. And the drop function in Rust is very similar to the destructor in other languages. The pattern of deallocating values at the end of their lifetime is called RAII, or Resource Acquisition is Initialization. It was popularized in the C++ world, so if you have used RAII before, the Rust approach will be familiar to you. We pretty much covered the first 2 rules. We have our value, it has an owner, and when this owner goes out of scope, this value is deallocated. Alright, so far so good, but the third rule states that there can be only one owner at a time. That sounds a bit problematic. Like, what if we want to have 2 pointers to our string simultaneously? Let's actually explore that. If we create another variable, let's just call it s, and we just assign our input to it. So now our input points to our string, and our variable s also points to our string, because the pointer will just be copied in between the 2 variables. So we have just 2 numbers that are 2 memory addresses that point to the same string on the heap. We can already see that the compiler starts to complain about this, and the problem with this is that if we follow these rules, it states that when the owner goes out of scope, the value will be deallocated. In this case, we have 2 owners of our string. When they both go out of scope, they will try to deallocate our string. This is called a double free, and it can lead to memory corruption. It is a common bug in C programs, and it has led to some very serious security vulnerabilities. So by guaranteeing a single owner, Rust eliminates the possibility of a double free error. In this situation, the ownership of the string is moved to the variable s. So after we assign a new owner to the string, the variable input is no longer valid, and the compiler will not let us use it after this point here. If we go to the console and actually try to build our program, we will get a compilation error that says that here, when we pass our input to the readline function, we're actually borrowing a value. We'll explain what borrowing means later. So we're trying to borrow a value after it has been moved. And the compiler is nice enough to actually show us exactly where it's moved. So it was moved here when we assigned a new owner. And also it tells us that the move occurs because the input, which is a string, cannot be copied. Pretty much. It can be moved, but it can't be copied because it is a complex type that lives on the heap. What types can be copied? For example, if we had the same thing with just normal numbers, let's say we have the number a, which is 5, and then this 5 is a number whose size is known at compile time. It lives entirely on the stack. It makes no allocations to the heap. So now if we create another variable and we just assign the a to it, this is completely valid because it will copy the value 5 to this new location. So currently we have 2 5s. We don't have 2 pointers to the same 5, but the value itself is copied because, as I said, its size is known and it is trivial to be copied. So this is the difference between complex types like the string that live on the heap and simple types like numbers. All right, let's delete this real quick. And the same rules are valid for function calls, because if we define a function here and we just name it some function, and this function will accept a string. So type our function. So if instead of assigning our string to a new variable, we just call the sum function with our input, again, the compiler will not let us compile because the value is borrowed after a move. And now it tells us that we move the value when we call the function. That means that when we want to call this function, we move the ownership of our string to the variable s that is inside this function. And when this s goes out of scope at the end of the function, the string will be deallocated. So if we were to use this string down here, like this pointer is no longer valid. The string is not at this memory address, like we don't know what is there. We will get corrupted memory and our program will crash. So the Rust compiler prevents this error from ever happening by enforcing the single owner rule. That kind of means that we can't pass parameters to functions and then keep using them after this function returns. And that sounds like a big issue because pretty much every programming language would let us pass variables to functions and then keep using them after these functions return. To make sure that we can do that, Rust has a feature that's called borrowing. And we will explain borrowing in more detail in the next video.